All right, so let us continue. Follow the previous way. We can have the example. For example, you have the sample, and the sample with the sample size of 219, and the data here, they are inter-arrival times. Okay, so inter-arrival times of cars to drive a bank, and you have the interval 90 minutes. Okay, 90 minute peak low period. Well, think about inter-arrival times. Which distribution you expect? Normally, you will think perhaps exponential, right? And left actually we have exponential. But first of all, if we have the sample statistic, you have a mean and you have a median. Okay, and you have skewness. So first of all, they are not the same. Okay, they are not the same. So not symmetric. However, passive skewness, so skew right and right skewness. Up to now, if you use skewness, actually you can rule out negative skewness family of distribution. And furthermore, if we have a CV equal to 1 and only exponential, so up to now, almost stop. You can use CV close to 1 to have the suggestion of exponential. But if you guess exponential, is it sufficient? Maybe someone don't think so. So that's why we have the plot. If we have the plot here, so using Sturge's rule, you can have these. All right, so you should have the proper selection for K. But right now, we don't want to use the Sturge's rule to have the proper selection of K. But we have, for example, the possible value here to have the interval, and so that you can have the possible relative frequency to check the probability, and so that you have the probability by using the Hill-Square. And if you have this, what is the shape? What is the shape? Of course, the shape of exponential. So this one somehow like ensures the selection of exponential. And also using the box plot, you have a plot here. So of course, you have the non-symmetric one, and also you have positive skewness. All of these ensure exponential. About this, is it okay? All right, so this one suggests you to have the choice of exponential. And now, actually, you have the discrete data, and you have the sample size. And this is the item demand. All right, and the same, you have a sample mean greater than median, and etc. So you should have the right skewness. And using lattice ratio, if you can follow the definition to have the lattice ratio, and lattice ratio greater than 1, and you should use negative binomial or geometry. Okay, now negative binomial or geometry, if you want to tell which one is true, so you should have a plot. Likewise, this plot suggests geometry, so it doesn't mean you need to have the negative binomial, because negative binomial asks you to have 2 parameter, and this one only 1 parameter. If you want to have the easier way to determine the parameter, of course, it's, geometry will be a good choice. All right, so the same if you have the data, and also based on the data, you can have the statistic. Even right now, we don't have the data. In fact, you can refer to the task book. Refer to the task book, and then you can have the data. Based on the data, you can have the statistic. Okay, so you can follow the data in the task book, and then you can have these. And I do not check all the details. In fact, later we can directly have some software. Use the software can make things easier. So later we have the possible software for you to have the calculation for statistics or some other further way to check the reason why we need to choose the family of a distribution to support you to have the possible selection. And next one, you have the multimodal. For example, two local modes. If you have these, you can try to think about which distribution may have the multiple modes. If you can have the multiple modes distribution, possibly you can choose it. But sometimes it is not really hard to have the multimodal distribution. If so, how to do? You can have the weighted sum. Weighted sum of some family of distribution, but by proper shifting. And superposition of the two perhaps can result in two local modes, for example, the current curve. All right, so for this one, actually, maybe you don't have the standard solution, but you can try to use a way to have the possible distribution based on the proper modification. And that's it. So this is a way to hypothesizing family of a distribution. Up to now, is it okay? If it is okay, let me continue. The next one, we need to estimate parameters. So estimate parameter, in the previous discussion, we have MLE. So of course, we will already have MLE. All right, and actually we have the way to have the calculation. If we want to have MLE, why? Because provide you the unique solution, and they are invariant. Actually, invariant means if you have some other way to change, it doesn't alter the solution, so invariant. And also asymptotically normal distributed. So if some distribution follow this, and then it's pretty easy to use MLE. And finally, it says strong consistent. All right, so it says if you have these, and it doesn't mean weak consistent and ask you to use these. For all of the reasons here, and we prefer using MLE, so you can try MLE for sure. But how to have MLE? In the previous tables, you have the MLE. As for how to derive MLE, this is the purpose of the current discussion. So let us check it. It says you have the hypothesized distribution. That says the selected distribution. And right now we want to fit the parameters. So of course we need to estimate its parameters. And previously we have some possible method, including MLE, but not MLE only. We can have the moment matching. Okay, moment matching. Moment matching code method of moment simply currently, and we want to check the dispute the estimator is unbiased or not. So unbiased, perhaps it is the key point, and also the least squares, and you can based on this square to choose some possible one. And Percy, we already know good statistic property, so that's why we use MLE. And this one, okay to justify some tasks. And this one, sometimes you will feel intuitive. Okay, and also allow you to perform sensitivity analysis. So for many reasons, we prefer MLE. If we want to check MLE, what it means, of course, we should have the sample data. Use the sample data, we want to choose one parameter so that maximize some of the probability. So most likely, that is make it possible with the large enough probability. If you can ensure this, and then that one serves the beta estimation of the parameter. As for the approach, we can have the following illustration. First of all, think about this. Discrete distribution. If we have a discrete distribution, for example, P sub theta to serve as the PMF. And if we want to do the result, we use PMF here and substitute all the observations so that you have the product form. With the product form, this function is called likelihood function. And if you have the likelihood function, we want to choose theta so that maximize the current probability given here. And how to do? You can have the direct differentiation or taking logarithm. Then you have the differentiation with respect to each item, and then try to make sure can you have the possible value for theta so that you can maximize the likelihood function or log likelihood function. Okay, so think about this. How to do? Okay, so many way, but you can have the direct differentiation or the indirect differentiation through taking logarithms first and then taking differentiation, and so that you can have the way to determine the possible value for theta. So in the following, we can have this one to serve as the illustration. And actually, for continuous or discrete one, all are valid. So let's check how to do. Wait a moment, maybe. We'll jump to the example here first, and so that we have the feeling how to implement the MLE. Right now, we switch back to the continuous one. So continuous one, of course, we based on PDF. So likelihood function is the product form. I substitute the observation to the position x. So 1, 2, to n, and you have these. By taking logarithm, we have these. And if you have these known beta, so perform this differentiation with respect to beta. And solve it, we have these. So it says about beta, how to estimate, we can use sample mean. if we want to ensure this provide you the solution, you can perform second you can try to get second derivative. All right, and also you have the choice. Substitute the choice into the second derivative. You have negative. Negative means this. So you have the maximum value. So of course, this point ensure some maximum value. So of course, it is the solution of MLE. If you have the solution of MLE, and then you can use sample mean to estimate beta, and that's it. So that's why in the previous discussion, for MLE of exponential, we can use sample mean directly. And in fact, if we have that one, even you have the estimation, and this one, something like you can have the confidence interval. But how to have the standard deviation, this one, sorry, how to have variance, you can use this way to have a variance and substitute into this, and so that this way can directly have the construction. All right, so this one, sample variance, use the formula here. As for the reason why, I don't have any idea. So if we are told this is a sample variance, we just follow this, you have the calculation and substitute into this. And so that this one serves the interval. So you can use the interval to check how close the selected parameter theta is. So you can use a way to construct the interval, and so that you can measure good or not. If good, you can use it. Okay, so we should switch back if you want to have the complete interval. Okay, so that's it. This is a way to perform MLE. And we have the first example using continuous distribution by checking exponential. Up to now, is it okay for you? So let me nominate some of you to make sure, okay or not. So first of all, how about this? Let me check. Dazong, is it okay for you? Or any question? Are you there? Oh, okay. Got it. Okay, no problem. And Diego, is it okay for you? So let me wait for the feedback from Diego. Diego says some parts are not clear. Oh, okay. So you will try after reviews, right? Okay, so maybe I just follow your suggestion. Even you have some parts unclear, but I continue for the illustration. And likewise, any other one have any possible questions? If no, let's check MLE for discrete distribution. Discrete distribution by using, for example, geometry, right? So geometry follow the form and substitute sample data to replace S, and so then you have this one, likelihood function. And if I want to perform the result, we need to take logarithm. So we have these. Once you have this one, you can perform differentiation to have this and set it to 0. You will have the solution. And this solution the same as the solution in the table. So that's why we have that. Well, the same, if I want to confirm, we need to perform second derivative and substitute the choice to make sure you have negative. But this one negative, it says it doesn't mean to check all the P. It doesn't mean the specific P. It valid for all the P. So of course you will always have the solution, and so that you have the choice for MLE. Okay, so that's it. This is the second example to let you perform actually the methodology to get the MLE. And that's why you can follow the previous suggestion to have the confidence interval. And so that you have these to serve as a confidence interval. It says the confidence interval for the parameter, and choose one among the interval. Any point within the interval actually can be selected, but we select the value using the MLE. All right, so this is the maximum likelihood. Up to now, is it okay? Okay, so I assume okay for you guys. Okay, wait a moment, let me check. Oh, thank you for your feedback. Okay, and next one, data check activity 3. Let us determine how representative the Philly distributions are. So how to do? Actually, we have many techniques to assist us to have the checking, determine how representative the Philly distributions are. So data check, what are possible techniques? Well, about the Philly distribution, of course, not perfectly correct, but at least we need to make sure. Is it okay? If I want to check these, here we have some heuristic procedures. First of all, we can use plot. What kind of plot? Density heat squared over plot, or frequency comparison. Later we can check this one. And next one, you can have the difference plot based on distribution function. And finally, you can have the probability plot to have the difference. First of all, for continuous data, this one using Philly distribution. Okay, for continuous one. Okay, wait a moment. So you can use the Philly one to have the plot. So the plot, actually, this is a continuous one. So something like you have PDF. Okay. And also you can have the histogram. As for the histogram, how to have the histogram? It says you can use this one to have the histogram. The width delta B and the possible estimate of a probability. Okay, and multiply and so that you have the histogram. All right, so the histogram actually something like serve as a quantization. Okay, quantization multiply the width to have the histogram, and so that this one serve as the way to check the shape of the PDF. Okay, and put them together. This one you can call you have the density histogram over plot, right? But actually, if we want to have the histogram, it doesn't mean we need to use a way. In fact, you can use the statistic for interval for within the interval, and then you have the relative frequency based on the relative frequency to have the histogram. And later we will use this way to have the relative frequency. But right now we use density function and use the histogram and put them together to make sure it's okay. All right. If we want to calculate, of course, this is a way. And actually, no need to have the calculation, but simply have the accumulation. You still can have the histogram. And next one, we can have the frequency comparison. For frequency comparison, you have the interval already, right? And you can have the observed portion. This one actually, this is the code, actually the way of relative frequency by using observation. However, next one, we can have the calculation directly. All right, and put them together and so that you have the way to check, right? And based on the R sub j based on the fitted one to have the calculation, and the H sub j based on the observation from the sample data. So put them together if they're almost the same or have the same trend, we will accept. Okay, so this is the frequency comparison. And previous one, we have a density histogram over plot. These are the two ways to check accurate or not, or how representative the selected distribution is. All right, so this is the first one. About the first one is okay. Even for the second one, we don't have the plot directly, but you can check the taskable and then you will have the plot. Is it okay? If it is okay, and then you can apply the same way to the discrete data, but we check frequency simply. For frequency, Hj the same, and Rj actually it is the approximated by using the fitted function. So it's really easy. This one, the same, put them together to have the relative frequency comparison. I think you guys should understand. Currently, relative frequency have two ways to have a relative frequency. First way and second way. Okay, and same for continuous one. We have a two way to have the measure of a relative frequency. All right. If both of them agree, so it says it should be correct. So we use this way to show the plot relative frequency. All right, so for this one, we don't have the density of histogram. All right, we just show the relative frequency comparison, and that's it. And actually, all the details within the taskforce, I just use slide to illustrate how to do. So it doesn't mean I contain all the details in the slides. I just try to illustrate how to do, and then you have some idea. So it doesn't mean I provide all the details. So if you want to have all the details, you can look up the taskforce to have all possible details there. And that's it. So this is the plot. Actually, next plot, it is called distribution function difference plot. Distribution function difference. So it says you should have two distribution functions. And right now, how to have the distribution function so that we can have the difference. So first of all, you can have the empirical CDF. And also you can use a way to define the actually that one this one it is a fitted one, and this one the empirical one. So fitted one and empirical one, try to find the difference. Of course, if they are the same, so you should have a 0, and so that we can check difference. And currently you have two examples, continuous one and the discrete one, and checking the difference of the two distribution functions, you will find still acceptable because almost 0. Right, for these and for these, so of course acceptable. Okay, so this is the second one, second plot, second type of, actually the second type of a plot, distribution function difference plot. Okay, the same. I start here and try to ask you guys any questions. So Junting, is it okay for you? Okay, so really direct, so no problem. So let me continue. And next one about plot, probability plot. We may have a PP plot and QQ plot. And let me show you this. QQ plot, quantile versus quantile. From different way to have the quantile, so that you have the plot. Normally, you should have this line to serve as the best fit. Up to now, looks okay. And PP plot probability versus probability. And the same, you should have a line. So you should have some example like this to have the good choice. However, let's check how to have the definition first. Right now, we have the observation and also try to have the increasing order to show the data. All right, so if we have these empirical CDF, empirical CDF can use a way to have a CDF. Normally, it should be these, but we can try to slightly have the difference minus a half. to serve as the empirical CDF. And also you have the fitted CDF. Right? So right now you have two. And actually find difference can use the current definition for fitted one and empirical one. So we've done that previously. But right now we want to use the two. And the two, in fact, how to find probability? If I want to find probability, this one, using fitted one to have a probability if we have a sample I. And also you can have the empirical one. Okay. And if you have the fitted one and empirical one, right now we have the plot using the pair. Empirical one and fitted one using the CDF. And so that these plots let us have a probability versus probability. And then it is called the PP plot. Up to now, is it okay? If you don't like the current pair, I mean the order of the current pair, you can try to reverse it. For example, you can have the fitted one first and then empirical one. Still okay. So right now, the task for illustrate, we use empirical one, then fitted one. And this one, if you want to have the way to have the result, you see, with the E and then F. So it's really easy to memorize the order. If you don't like it, you can have a fitted one and then empirical one. Something like you reverse the alphabets E and F. So I think still okay. However, EF maybe is an increasing order. Perhaps it is really easy to memorize. Okay, so empirical one, then fitted one. And also, how to have the quantile. If you want to quantile, taking inverse function based on the fitted distribution for the pair here. And so that you have this. And this one, it is the data. And so that if you have this, by taking the inverse function, the inverse fitted function, so you have these. And these plots allow you to have the quantile versus quantile. And so that you have the QQ plot. Okay, so this is a way to have the inverse function so that you have the quantile versus quantile plot. Sometimes we have the direct meaning, how to have the map to the quantile properly. For example, right now, we use the figure to show you the results. The empirical one, the fitted one, right? And how to have the probability. You can try to have the selection for pair, to have the probability. So this is a PP plot or QQ plot. Okay, so this is the first one. So let me make sure, is it okay? Oh, sorry. Please, maybe let me have the new definition again. This one, it should be the given, maybe it is called a quantile, but we have a probability. This one, it is a P plot. And this one, given a same probability but corresponding to the quantile. So it is a QQ plot. Okay, because we have the fitted one and the empirical one, so we can pass on the two CDF to have the quantile or to have the probability versus probability by given the attribute point, so that you have the pair of probability, a pair of quantile, so that this is a QQ and this is a PP plot. If we have this, it doesn't mean we need to have the inverse function. We just have the direct interpretation if you can find possibly the corresponding point for Q and P. And actually, you can have some example so that you can have a QQPP plot. Wait a moment. Oh, you mean QQ and PP? Oh, yes. Well, wait a moment. Let me try to look up the task book. If you have the task book, I just follow this. So you guys wait a moment. Actually, you can look up task book on page 326. All right, so you can have some results here. All right, with the results here, you may have some selection of exponential. For example, for the drive up inter-arrival time, so you can have the exponential. And also you can have the fitted parameter beta. So if you have these, then you have the fitted one. Okay, once you have the fitted one, then you can have this curve, fitted one. And as for the empirical one, which one we use? This one. Right? So you can have the empirical one. And once we have those, and then you can use a way to have the PP plot. This way you can have the PP plot. And this way you can have This one you can have the QQ plot. All right, so you just follow that definition. However, you need to have some given data. Actually, previously I just let you have the given data. So that's it, right? So I think right now Panka understand me, right? And same for the other students. In fact, we should have some data set. Okay, so actually we will have the data set, but I skip some of the data set because those data set described in the task force, so you can check that. All right, so if you understand me, and then we can have this. This one, this is a theory. The theoretical approach. Okay, so we don't have the real, actually we don't have the direct calculation, but we follow the formula to have the empirical one, to have the fitted one. And here I just try to illustrate how to have many Q. For example, I have many vertical line to have Q pair, Q pair, and Q pair. Collect all the Q pairs, you can have the QQ plot. And furthermore, use a way to have the given points. Given points to allow you P and P and P and P here. So P, and O allow you to have collect all PP pairs. You will have the PP plot. So this is a theoretical way to have a PP and QQ. But the current one allow you to have this one actually same as the PP, the idea of PP. But about the QQ, we use the inverse function to get Q and Q. Even the second place, it is easier to have the sample data. But the first one seems to be you need to have the calculation. Okay, if you don't mind the calculation, sure, you have the quantile. And that way it is the quantile for sure. So here you should have the calculation. And of course, for the current way to have the mapping, you have the curve, and these curves serve as the calculation for sure. But it seems to me you don't have any calculation, but it is not true. You have the mapping, so same, you should have the calculation. All right, so you can have the easier way to have the mapping directly by using the function. Or you can have the curve to have the mapping. And both of them, they are the same. They try to illustrate, you can show them in pairs of probability or pairs of quantile. If they are matched, you should have the straight line here. And the same right now looks like straight line almost so acceptable. All right, so even acceptable right now, we try to check some phenomenon so that we know the behavior of PP and QQ. PP or QQ, so that that'll check why we have the amplified tail. amplify the middle or tail. So look at this. If we have the tail, the difference around tails. So how to find the PP? Look at this. PP. So how about the difference? Small difference. So small difference, right? And how about QQ? We emphasize the tail. Large difference. So that's why large difference. If you have the difference around tails, so QQ amplify the difference of tails, not PP. Okay, so the current slide illustrates this. The next one, if we have a middle, right? And how about this? How about QQ? Small. And how about PP? Difference huge for PP. Difference huge for PP, so you can have the phenomenon for PP here. So PP can amplify the difference of middles. Okay, that's it. So the two figures just want to that you guys know PP plot and QQ plot can amplify the difference of different segments. For tail, amplified by QQ. For the middle, amplified by PP. About the two slides, is it okay for you? Here I use the general approach to have a PP and QQ. So it doesn't mean I use the previous inverse function to have the calculation, because I just try to illustrate the idea. So this idea to have the mapping using the curve. So that's why I use the general approach directly rather than the calculation. All right, so about this, up to now, is it okay for you? Panca, okay for you? Okay, thank you. And how about Junting? How about this, Junting? Okay, good. So let me continue. So up to now, we use heuristic approach by having some plots. Okay, so I think you guys will have some image about the plots. Next one, we can have the test, but let us take a break first. Actually, we should have take a break a bit earlier, but right now, let us take a break. Sam, take a 5-minute break, and after that, we continue. Okay, take a rest for you guys.